on Chapter 3.5, Implicit Differentiation. Honestly, this is nothing more than an application of the chain rule. It's just sometimes in mathematics we're faced with equations involving two variables, as you can sort of see illustrated here. X squared plus y squared equals 25. X squared plus y squared, the quantity squared, equals x squared minus y squared, or even x equals the tangent of y. In some cases, we can solve the equation for y explicitly in terms of x, and other times we just can't. But in both cases, thinking about differentiation implicitly will allow us to get at how the quantity y changes with respect to a change in x. We think about y as being a function of x, but we don't know what that function is. So perhaps let's start with the simplest one, x squared plus y squared equals 25. That represents the circle that you see almost drawn on your screen. When you solve for y, you get two possibilities. Y equals plus or minus the square root of 25 minus x squared. The upper half of the circle is represented by the positive solution. Y equals the square root of 25 minus x squared. The lower half of the circle is represented by the negative solution. So even though the original equation represents both halves of the circle simultaneously, we can break it down into two explicit functions. The equation x squared plus y squared equals 25, here y is implicitly a function of x, and it changes as x changes. Our goal is to find what that rate of change is. We're going to do it two ways. First, let's work with the upper half circle and the explicit representation. We know that y is the square root of 25 minus x squared, so we want to take the derivative of that. In order to take the derivative, we have a composition of functions happening here. We're going to have to use the chain rule. The inside of the function, the inside of the composition is u equal 25 minus x squared. The outside is y equals u to the 1/2. To apply the chain rule, we need to take the derivative of each of our pieces, the inside and outside function. So du dx, the derivative of u with respect to x, is negative 2x, and dy du, the derivative of y with respect to u, uses the power rule, 1/2 u to the negative 1/2. That means when we want to write down what y prime is, remembering that we're thinking y as a function of x, so really this is dy dx, that's going to be the derivative of y with respect to u times the derivative of u with respect to x. Those are the two pieces we just computed, so we can substitute what we found in. So y prime is going to be 1/2 u to the negative 1/2 times negative 2x. Simplifying and replacing the u with the function of x, we get negative 2x in the numerator divided by 2 times the square root of 25 minus x squared in the denominator. There's a common factor of 2 between the numerator and denominator we can divide out by, leaving us with our final simplified form of negative x over the square root of 25 minus x squared. So that's how we do the problem explicitly. We can now try the problem again implicitly. What do I mean by that? We're not solving for y as a function of x, we're thinking of y as a function of x. And it's going to take on the role of the inside function in the chain rule. So let's try it, and let me show you what I mean. We're going to start by taking the derivative of both sides of the original equation, namely x squared plus y squared equals 25. We're taking this derivative with respect to x, and this is where the Leibniz notation is very handy. Somehow x is our independent variable, and when we know that y is also a variable, we're going to assume that y is a function of x. We just don't know what that function is. So we start by taking the derivative of both sides. On the left-hand side, the derivative of 2x is, the derivative of x squared is 2x. And I'm just going to write down the derivative of y squared because we're going to need to find that with the chain rule. The derivative of 25, since 25 is a constant, that derivative is going to be 0. Now, to take the derivative of y squared, we're going to use the chain rule. The inside function is y, because y is some kind of a function of x. The outside function is y squared. So when you take the derivative by the chain rule, we're trying to find the derivative with respect to x, so the derivative of y becomes dy dx. And the derivative of y squared, here when I take the derivative of what I've called v here, I'm taking it with respect to y. So v prime, or dv dy, ends up being 2y. The derivative of y squared is going to be the product of these two. This becomes 2x plus dy dx times 2y equals 0. Again, dy dx is what we're looking for. We're looking for the rate of change of y with respect to x. So let's solve for that derivative by isolating it on the left-hand side. Subtract 2x from both sides, and then divide both sides by the coefficient of dy dx, namely 2y. That gives us negative 2x divided by 2y. The factors of 2's will cancel from the numerator and the denominator, giving us dy dx equals negative x divided by y. Now you might want to compare your answers between what we got explicitly and what we got implicitly. Notice they both have a negative x in the numerator. That's great. And over here I have a square root of 25 minus x squared in the denominator. Over here I have a y. But remember, at least in the case when we're looking at the upper half of the circle, what y was, it was the square root of 25 minus x squared. So, at least for the upper half of the circle, we got the same answer. But we also got the answer for the lower half of the circle at the same time over here, because I didn't have to tell you which case I was in. So, that is implicit differentiation. For the next problem, I want to look at the lemniscate, great word, whose equation is x squared plus y squared, the quantity squared, equals x squared minus y squared. So for this particular graph, unfortunately, or maybe fortunately, I don't know, it really is nigh on impossible to explicitly solve for y. So if your calculus teacher asked you to find the slope of the tangent line for any point on the curve, you would have to do this one implicitly. So again, you're thinking of y as some kind of a function of x, but this time I can't solve for what that function is going to be. So you're going to need to take the derivative of both sides of this equation, and you are going to have to apply the chain rule a bunch of times. There's going to have to be a chain rule that happens here, because I have some interesting stuff squared. There's going to have to be a chain rule that happens here, because remember, y is a function of x, so that's going to end up needing a chain rule there. And you are also going to need a chain rule when you take the derivative of negative y squared over here. So my suggestion to you is to pause the video right now and try to take that derivative on your own. Here we go. If you did this problem correctly, you should have gotten dy dx equals 2x minus 4x times the quantity x squared plus y squared divided by 2y minus 4y times the quantity x squared plus y squared. So if you have any questions, make sure to ask me and we can talk about it again. But I really want you to try this on your own. Our last problem for today is to look at x equals the tangent of y. This, if you solved it explicitly, would give you y as the inverse function to tangent, which, just to be clear, I'm going to call arctangent rather than tangent to the negative 1. So if we knew the derivative of arctangent, there would be no reason to solve this implicitly. But because we don't, if I can take the derivative of x equals tangent of y implicitly, it will give us the derivative of what arctangent of x is. So let's do this as our last problem for the day. So we're going to take the derivative of both sides with respect to x of the function x equals tangent of y. To do the tangent of y, remember y is this function of x we have to take the derivative of with respect to x. We're going to have to use the chain rule. The inside function is going to be y. The outside function is tangent of y. When you take the derivative of the inside function with respect to x, you get dy dx. When you take the derivative of the outside function with respect to y, you get secant squared y. So when we go ahead and take the derivative of the equation, the derivative of x is 1, and the derivative of tangent of y, based on the chain rule work we did, is going to be secant squared of y times dy dx. dy dx is what we're looking for. That's what you want to solve. So we can divide both sides by secant squared x. And remember, secant squared is just 1 over cosine squared. So this is 1 divided by 1 over cosine squared. And we can simplify dy dx to be the cosine squared of y. And if you want to get rid of that y right now, it's going to be cosine squared of, I should have said arctangent of x. Another way of writing it is as tangent inverse of x. And here, this is a functional inverse as opposed to a multiplicative inverse where the exponent to the negative 1 means take 1 over. That's not too pretty yet, but I want you to pull out your trig knowledge and recall what tangent inverse of x represents. It's an angle theta such that the tangent of theta equals x. And as we did last time, we want to draw a right triangle with this angle theta so that the tangent of this angle takes on the value x. So one way of doing this is by assigning the opposite edge the value of x and the adjacent edge the value of 1, because tangent is opposite over adjacent. We can now figure out what the hypotenuse is by using the Pythagorean theorem, and you should get that the hypotenuse is the square root of 1 plus x squared. So to complete the problem, we're looking for the cosine squared of this angle theta. Well, here's this angle theta, and the cosine is adjacent over hypotenuse. So if I take the adjacent over hypotenuse and I square it, that will give me the answer. The good news is when I square a square root, I end up with 1 over 1 plus x squared. So the conclusion of all of this is we've just found the derivative of the arctangent function, and the derivative of the arctangent of x is 1 over 1 plus x squared. I hope this gives you enough to go finish your homework problems. I hope you see that implicit differentiation is really nothing more than applying the chain rule. And I hope you're practicing your chain rules because it's going to be important from now on. Thanks for your time.